Welcome to the webinar 10, focused on cyber-physical systems of the webinar series of data science, machine learning, and AI, applications and opportunities. A cyber-physical system is an embodiment of physical entities and accompanying processes with computational capabilities to link the physical world of sensors and actuators with the virtual world of information processing. Cyber-physical systems, or in short, CPS, are complex systems capable of cognition, communication, computation, and control, which is in short written as 4C. Consequently, CPS has four main components with unique functions. They are physical infrastructure consisting of sensor for sensing the stimuli to curate raw data, actuators for responding to the stimuli, and a computational intelligence platform for computing the response contingent upon the stimuli. And finally, a network that interconnects all of them. The development of intelligent computational techniques, or the computational component of the CPS that are capable of harnessing the CPS sensor data that has been curated, is the focus of today's webinar. And we have two outstanding panelists for today's webinar. First, we have Dr. Karthik Dantu, who is an associate professor in computer science and engineering at University at Buffalo. He received his PhD in computer science from USC and was a postdoctoral fellow at EECS at Harvard from 2010 to 2013. His interests lie in perception and coordination challenges in mobile systems and multi-robot systems. He leads the distributed robotics and networked embedded sensing, or drones lab at UB, and co-directs the reliable mobile systems lab, and is a member of Community of Excellence in the Sustainable Manufacturing and Advanced Robotics Technology, or SMART, College of Engineering at UB. He is a recipient of the NSF Career Award in 2019 and the Best Paper Runner-up from ACM EECS 2019 and IPSN 2012. Outside of work, he is an avid fan of cricket and American football. The second panelist that we have today is Dr. Ashis Banerjee, who is an associate professor of industrial and systems engineering and mechanical engineering at the University of Washington, Seattle. Prior to joining University of Washington faculty, he was a research scientist in the complex systems engineering lab at GE Global Research. Before joining GE Global Research, he was a research scientist and postdoctoral associate at MIT. He obtained his PhD and MS in mechanical engineering from the University of Maryland, College Park, and BTech in manufacturing science and engineering from Indian Institute of Technology, Kharagpur. Dr. Banerjee has published more than 50 articles in peer-reviewed journals and conference proceedings. He has received several honors, including the 2021 IAOTP Top Engineer of the Decade Award, 2019 Amazon Research Award, 2012 Most Cited Paper Award from CAD Journal, and 2009 Best Dissertation Award from the Department of Mechanical Engineering at University at Maryland, and 2009 George Harkalis' Outstanding Systems Engineering Graduate Student Award too. His research interest includes smart manufacturing, predictive analytics using statistical and topological learning, and autonomous multi-robot systems. So with that, let me welcome Karthik Dantu for his remark and his comments on today's webinar.
Thank you, Rahul. Let me share my screen. Okay. Thanks again, Rahul, for the generous introduction. Like Rahul mentioned, my name is Karthik. I'm an associate professor at the University of Buffalo. I lead the drones lab. Like any faculty member, all the work we do is basically the work of my students and collaborators. So I have listed the students I've worked with in the top row, the faculty I collaborate with in the bottom row. I will, and a lot of the information is available on our website as well as the papers are available if you are interested. So like Rahul mentioned, my interest in particular, so CPS is a very broad area. I work in multi-robot systems, and in particular, I will focus mostly on the applications in unmanned aerial vehicles in the stock. Even in that, I'm a computer scientist by training, so my interests are in perception and coordination, and I will describe some of the projects that happened that have been done in my lab. UAVs are quite an exciting cyber-physical systems platform. Just the way we have been able to condense the sensing and computing on these mobile systems, they are used for a variety of applications, including lots of startups in those spaces. So infrastructure inspection is one of them where we have, where you want to inspect a bridge or an oil well or any large structure that was previously difficult to inspect. There are startups like Skyward and Atlas Dynamics in this space. Package delivery has received a lot of attention in the form of Amazon Prime Air, or more recently Zipline, which delivers medical supplies. Precision agriculture is another major area where UAVs have been used quite a bit, and there are startups both in Europe and in the US like Gamaya and Microsense. The broad area of autonomous vehicles, of course, has exploded in the last 10 years. Lots of companies, including, I'm showing you the Ollie autonomous bus here, which is a level 5 autonomous bus. We have one of these at UB. Military, of course, uses quite a bit of unmanned aerial vehicles for surveillance, reconnaissance, search and rescue, etc. And something that has taken off more recently is urban air mobility to mitigate the problem of traffic. Can we use unmanned aerial vehicles for transportation in small to medium distances, like in a downtown, in an urban area, etc. And that's a hot topic of research. There are lots of driving factors to use one or more UAVs together, one or more unmanned aerial vehicles together to solve a problem. And these are all the applications. So as a computer scientist, so what is interesting to me is to find applications of autonomy and how do you enable autonomy in each of these places. I view autonomy the following way. This is probably a very general picture. Usually autonomy means you want to make the robot, in this case, an aerial vehicle, think for itself. And that starts with perception. So being able to, let me see if I can get a laser pointer. There you go. So you first be able to perceive the real world. So use a set of sensors on board that sees the real world. And out of the sensing comes some information that you want, or fitting some model that you have of the real world. From there, many times you do spatial reasoning, which is localization or mapping, meaning I want to identify where I am with respect to the environment and what is around me from where I am seeing. Those are the joint problems of localization and mapping. And this you can use to do some form of planning. So let's say I want to go from point A to point B, being able to understand where point A is in the global map and go to point B in the global map is what the problem of planning is. So once you have a map and location, you can plan, and then you execute that using some form of motion control. These days, the popular platform is quadrotor, so they have some kinematics, and you execute that using that. Or there are newer forms, especially applications such as urban air mobility or package delivery. The companies have been building novel forms of aerial vehicles that suit that particular application. So you realize that in a certain way. So I show this because my interests are in perception. So I will talk a little bit about perception. And then coordination, where multiple UAVs or multiple autonomous vehicles talk to each other and coordinate in some way. And that is a second application. So let me jump into perception. In particular, I will talk about spatial perception, right? So how do you look at space? So uh, even in that, what I'm interested in is something called SLAM, which is simultaneous localization mapping. So these two problems I mentioned of where I am with respect to the world and what is around me from where I'm seeing, those are sort of joint problems, and together you solve them, and that joint problem is called SLAM. More recently, we've been using vision or visual sensors for SLAM. So I will talk about visual SLAM. And then I will talk about some pieces of multi-robot coordination that we have done. Okay. So before I jump in, I don't, I wasn't sure how much of a background the audience has in visual SLAM. So here is a general pipeline of how visual SLAM works, right? So your UAV receives an image. So it has a camera on board. Usually cameras can be just color cameras or depth cameras or RGBD cameras, meaning I get both color and depth. You take the image, you do some feature detection. In this case, I'm showing you one image here, and the next image is after the robot moved a little bit to the second image here. So in the first image, you do the circles, they roughly show you the features that are being detected. Let's say sift or surf or orb or or corners or something like that. And then on adjacent images, you do feature matching. So you try and see what features correspond to other features in the following images. Using some camera geometry, if you understand camera geometry, you do odometry estimation. So when I take a picture, I move, I take another picture, I do feature matching between the two. I understand in pixel space how much the world has moved. From that, I can back calculate how much my robot has moved. And that is essentially odometry estimation. It involves just camera geometry. If you understand multi-view camera geometry, then you can back calculate that. So as the robot is moving in the environment, the camera is taking many pictures. I do this odometry of, I connect image one and image two and image three, etc. And I get a trajectory of the robot, right? So I'm now getting the location of the robot, and I'm getting the features which form the map of the environment. So I'm solving the simultaneous problem of localization mapping in that way. Occasionally, I come back to a place where I was before, so I see the same features. And then in the map, I do something called loop closure. So I match the features and I connect the map points, and that requires some optimization to run, which is loop closure detection. So that is a 2-minute view of visual SLAM. Visual SLAM is a sub area in perception in robotics, computer vision. It has been in research for now, I want to say, more than a decade. There has been significant advances, but there exist some challenges as well, right? So one challenge is that of perceptual aliasing. If you're only dependent on image features, you might be traveling in structures that look very similar, right? Let's say an urban area, maybe two corners of the building look very similar, or inside a building, when you're going down a corridor, the patterns look very repetitive, where you see a door and then some wall and a door. So you can get confused between two locations because they look visually very similar. And that has been a consistent problem. I will show you in the next slide one solution we have. There can be various other things. Another challenge, so we are using fancier cameras, we are using higher resolution, more points in a point cloud from a depth camera, etc. So map size becomes a problem. As I build this map, it just grows exponentially. And on a UAV, it's challenging to maintain the map and reason with the whole map. And so you have to do something to offset the map size, and that's another challenge. And we will come to that. So those are two problems I will talk about with respect to visual SLAM. So the solution to perceptual aliasing, so in the image space, there are repetitions and it's hard to distinguish. So almost always the answer is use some other sensor. Can I use some other form of sensing to compensate for this issue? So our idea was to use Wi-Fi. So indoors, almost all buildings have Wi-Fi and they are densely connected with Wi-Fi. We came up with the idea of using simple signal strength. So if you at any point look up all the access points you can see in a building, you can see in the order of 10 to 15. That's how dense it needs to be to accommodate a reasonable office or university building given the population. So you can get the received signal strength from each of the access points, and I can compile that as a vector and use that as a signature for the location I am in. So even though, let's say I'm traveling in a corridor and the diagonally opposite sides of a corridor are visually similar, this wireless signal strength is very different because I can see different access points at one location, other access points at the other. So I'll play this video, and that shows you 2 runs of a well-known visual mapping algorithm called ARPSLAM2. One is the vanilla version. The second is the one instrumented with our Wi-Fi sensing. So we annotate each image with the wireless signal and then use that for distinguishing different locations, and therefore are able to do better, are able to avoid perceptual aliasing in this case. Okay, I don't know why the video is not playing. There you go. So this is, in this case, a ground robot that's traveling. On the right-hand side is the end map that will be built. So the left box is showing you vanilla ARPSLAM, the default ARPSLAM, and on the right side, it's showing you the Wi-Fi augmented ARPSLAM. So this is a current view of the map being built, right? So we will just run this a little faster so that, you know, we don't need to wait for as long as it runs. So this is the color image. These are the features detected, and these are the point clouds that are being aligned to build the map, right? So it's now making a first turn. You're going down the second corridor. The blue triangles are the images that are taken. It's the camera poses, and the green edge is the odometry that's being calculated between the camera poses. So you go around. And possibly now on the left side, what vanilla ARPSLAM does is it confuses between diagonally opposite ends of the corridor. And so it just folds the map. So it looks very ugly, but what has happened is it thinks the diagonally opposite ends of the corridors are the same. And so the map is folded, whereas our Wi-Fi assisted mapping algorithm does not confuse that, and it's able to distinguish it quite well. Yeah, so the end map that is produced is actually quite incorrect in the default case, whereas you can see what we build is, so you can see the 4 corridors, we did a whole loop, and we came back to the place where we started. We have a multi-robot version of this as well. So for multi-agent mapping, we have another version. So this was in Autonomous Robots in 2019, I think. And we had an ICRA paper on the multi-robot mapping, which is also submitted to IGRR now and is in review. The second problem I mentioned was that of map size and resources. So as the map grows, the amount of memory it takes on the device, as well as how much computing I need to do to look at all of the map grows. And so this is a challenge for most embedded devices if you're looking at augmented reality applications, as well as UAV or robot applications where the resources on a robot are limited. So our solution to that was to offload or run some of the components of the SLAM system remotely. Of course, that sounds straightforward. You can take some pieces, run it remotely. The challenge, though, is a SLAM system very monolithic. They work with this large data structure, which is the map, and they are very time sensitive, right? So as I get images, I need to process them. So if I get images at 30 frames per second, I need to process them in the 33 milliseconds I have. And talking to a remote place and coming back is usually challenging. So you have to be very careful about how you design that. to make sure it runs on time, right? So here is a view. So this is the memory usage. If I run ARBSLAM on a device, as you can see over time, the map size grows. This is the CPU usage. It's taking about 30 to 40% of the CPU, and that also sort of grows over time, not as drastically as the memory, but we've observed it also grows. So our objective is to not have it grow, right? We can't give up all the resources for SLAM, which is a single service on robot. We want to run many other things. So what we came up with was, like I said, this offload. So here is the regular SLAM algorithm. What we did was we split that. We run only tracking on the UAV. We run the local mapping and loop closure on others. So for this, we had to design another data structure called the local map. There's some communication, and these communications have to be timed exactly so that it works, all of it works in a timely fashion. Here is, I will just show you the results, right? So here is, again, the red and the green are the ARBSLAM running on two separate devices. The red is on a Jetson, which is an NVIDIA embedded board. The green is on a laptop, so it's an Intel processor. The blue and the corresponding brown lines are our version, the EdgeSLAM running on these platforms. So you can see the memory is constant. It does not grow over time, right? So that's the first thing achieved. This is the CPU. The blue and the brown are the CPU usage on the Jetson and the laptop correspondingly. You can see they're around, on the laptop, I think it's around 17%. On the Jetson, it's 22%, but much lower than what ARBSLAM does, that we accomplish that just by remotely offloading. Correspondingly, we don't lose any accuracy. That's the other side. When these timing issues occur, gradually you lose accuracy. You can see here the ARBSLAM has an error of 20 centimeters, EdgeSLAM has an error of 20 centimeters, modulo the standard deviations. Same thing with on the laptop. So we are able to maintain the same accuracy without the resource use that ARBSLAM does. So this was a Mobisys paper. We now have a transactions paper in submission. We also have a multi-agent version of this that is under works. It's almost done. That requires a lot more sort of effort in terms of coordinating everything. Okay, I think I'm running closer to time, so I will speed up. The second part of my talk is about coordination. So this was perception, particularly visual SLAM and how you can use that. So I've worked some amount with multi-UAV planning. Multi-UAV applications are difficult to work with just because deploying many UAVs and studying them is challenging. So one of the first things we did was to build a simulation environment. So multi-UAV applications have two things that you want to simulate well: the robot behavior, which a lot of the robot simulators do well, but also the networking behavior, which the robot simulators don't do well, but there are networking simulators that do well. So when doing multi-UAV applications, we wanted to put both of these together and get a realistic simulation. So we built something called UBANC. This is in the Journal of Microaerial Vehicles in 19. You are able to change the fidelity in this one, where I can be as realistic or less realistic in the networking aspects, or I can be as realistic or less realistic with the UAV simulation. In particular, we simulate Mavlink-based UAVs. So if you've used the modern drones, they come with these autopilots called PX4 or ArduPilot. Both those autopilots communicate using the Mavlink protocol. So we have a software in the loop simulation of that. And so we can give Mavlink commands that do this in a real fashion. For the network simulation, we do low fidelity simulation, meaning perfect communication, so I'd not worry about the networking, or high fidelity. So we've integrated our simulator with something called NS3, which is a state-of-the-art network simulator. We also have integrated with EMAIN, which is the AFRL, the Air Force Research Labs mobile ad hoc network simulator. So you can do very realistic network simulation. Okay, so what have we used this for, right? So if you one of the standard multi UAV things you want to do when you have multiple UAVs, you want to divide the tasks that you have among them. So this is the standard problem of task allocation. There are lots of solutions. One popular approach to doing task allocation is this came out of MIT. This is an approach called CBBA, consensus-based bundle adjustment. So this is a well-known algorithm. They guarantee, so CBBA guarantees that you will do not worse than 50% of the optimal when you formulate the problem in their way, right? So this is a very sort of theoretical result, and we wanted to see practically how well that does. So we configured the network simulator with multiple settings, and we ran CBBA, or a version of CBBA called ACBBA. And what we found is sort of surprising, I think. So if you, as you increase the number of agents, that's what is happening in the x-axis. The y-axis is the redundant assignments, meaning multiple UAVs deciding to do the same task, which is a bad thing, right? So that's suboptimal. This goes up quite a bit as you increase the number of agents well beyond the 50% optimality that they guarantee. This is because of losses in communication or interference, et cetera, which happens in the real world, but was not assumed in the ideal model. Again, these are the benefits of doing realistic simulation versus not using them. And a lot of the robot simulators do not do realistic network simulation. So we came up with an alternative. In this paper, we propose ways of delaying the communication and back off and so on that allow us to get back to closer to optimality. But the higher level point was, irrespective of what algorithm you use, it's important to use realistic simulation of both the network as well as the robot behavior to ensure correctness. The second problem we were thinking of, so one big issue with UAVs, if you have flown any UAVs, are the time of flight, right? So they carry the batteries which they use to fly, and almost always they're limited to something like 20 minutes of flight, and anything you can do to improve the flight time is a useful thing. So one of the things you want to do with a UAV is something called coverage path planning. Given an area, I want to cover the whole area, search in that area. So this can be for search and rescue or coverage or any of these problems. So we formulated an allied problem of minimum energy coverage path planning. So I want to use the minimum amount of energy to cover a given area. Something that's been studied in, not exactly, but in similar ways in other research. There was something called depth limited search, DLS, which was published in Journal of Field Robotics a few years ago. But we formulated this directly, and we measured the energy consumed by actual flights, and we modeled that in real life, and we came up with this algorithm called MEPP. Okay, I won't show this video. That's less interesting given the time. But the upshot is that our algorithm is able to beat the state of the art by 20 to 25% in energy. So you're saving 1/5 to 1/4 of your battery life while doing the same task using sort of a more direct energy aware approach. Sorry, this is not particularly interesting other than we have flown UAVs. So I can go forward. There you go. A final thing I'll touch on is this work I did recently on the DARPA offset project, which was interesting in that the objective of the project was to do end-to-end learning of multi-robot behavior. So you want to learn ways to for the robots to behave for a particular task. In this case, I want to search multiple buildings and find a target. And you are given a combination of UAVs and UGVs for this task. And you want to apply modern machine learning to do end-to-end learning. It's a very high-dimensional problem, very challenging. We came up with a couple of techniques to make it feasible. So one of them is using human intelligence. This has been a common approach if you looked at AlphaStar and some of these gaming multi-agent solutions. So what we do is we gamified this problem and made many users play that game, and then we learn from the strategies they use. The approach we use is something called neuroevolution. It comes from genetic algorithms. A version of it, we adapt a version of it to do the end-to-end learning. And we also, so okay, this is maybe a more detailed view. There, we spent some time in doing the exact encoding, decoding. That took some amount of time in terms of the input, output, encoding to get the exact things. And finally, being able to simulate these things at much faster than real time. Otherwise, you're not able to really learn as quickly as you want. And we came up with several solutions. There are multiple settings. If the environment is static, then it's a little easier. If the environment is dynamic, then you want to learn the dynamics a little better. So we had to do much more simulations, and the depth of the learned network is greater in this case, right? So again, these are some graphs with the real environment. We actually took our algorithm and deployed them outside Seattle, actually, with a swarm of 60 robots. And so we demonstrated this in real life as well, which was exciting for us to see the learned algorithms in action. Part of this exercise was that human gameplay. So building something where humans can interact with things came up with a separate set of challenges. And so we had to build some environment to reduce the dimensionality of what we show the human, because there's a lot of things that you can show the human. And that was part of the challenge. And also measure physiological use physiological sensors to measure exactly, understand exactly what the human is doing. Like, what is the human seeing with eye tracking? What is he thinking with like brain-computer interface and so on. So I'll stop there. Hopefully that gives us enough meat for discussion. I'll hand over to Ashis.
Thank you, Karthik. Thank you for showing very, very interesting and nice projects. Let's move on to the second panelist of today's webinar, Ashis.
Yep. Can you enable screen sharing?
Yes, I have made you a co-host, so you should be able to do that now.
Okay. Yeah, I think all of you can see my screen now. So first of all, thank you, Rahul, for organizing this exciting set of webinar series. So what I'm going to talk about are some other kinds of applications and opportunities of data science, machine learning, and AI in cyber-physical systems. I do some work in robotics, and some of the projects will cover that, but you'll see like other kinds of applications as well, from logistics, manufacturing, and so on, and even transportation. So I think Rahul has already made a detailed introduction of my background, so I won't spend too much time on that. But what I'd jump into is kind of the broad portfolio of CPS related research projects and topics that I have had the opportunity to work over the past 5-6 years. So as you can see, from various application domains with very different kinds of challenges. And as we go over some of those project summaries, those will become more clear. But I do want to highlight like the breadth and diverse nature of the possible applications of machine learning and AI, as well as the broad suite of technical and research challenges that they might address. Also, I'd like to highlight that in my group, which we call the Smarts Lab, we generally end up employing a wide variety of machine learning and AI tools. So it's not just deep learning, although deep learning forms a core component of what we do, but there are other aspects, including some overlap with the SLAM work that Karthik was talking about, also some components of reinforcement learning and other tools like topological analysis and Bayesian regression and so on that I don't think I'll have the time to get into today. So the way it structured the talk is I'll give like this very high level 3-4 minute overview of a few different projects, and I have deliberately chosen them to cover very different domains. So hopefully I'll be able to go over all of these in the next 18 minutes or so, but if not, I may have to end after covering maybe 3 of them, and we can like feel free to follow up with me to know more about what we are doing in some of the other projects. So the first one that I'll talk about is something that we worked on for a couple of years, and the project is now complete in some sense, where the goal was to look at whether robots can assist humans in reducing the ergonomic workload for people who are typically engaged in doing activities as a part of their daily job profile in warehouses or other logistic centers, which require, as you can see from this schematic, moving these heavy boxes and cartons. So something that you would expect in like an Amazon fulfillment center, Walmart center, and so on. So for a robot to be able to do that kind of an assistance of human associates or partners, first it needs to be able to perceive or figure out what activities the humans are actually doing, and then also associate with those identified activities some kind of a risk score, or in our case, just a very like discrete risk category of whether it's a low risk activity, medium or high risk, that kind of a thing. Now, why is this important? It has a huge potential impact on the health, the long-term health of the workers doing these types of activities. And this is just one statistic. It is a little bit dated, but the number is only going up, not going down. So it has been found, this report came out in the US Bureau of Labor Statistics in 2016, that the long-term impact of doing these activities leads to something called musculoskeletal disorders in as many as just the reported, the real number might be even higher, like more than almost 350,000 reported such cases in one single year, which of course would mean that you have a financial impact of the order of tens of billions of dollars in healthcare cost, in like lost productivity, and then potentially long-term care for the workers. And this is not even accounting for the fact the direct impact in the lives and families of the workers themselves. So we believe that if robots can accurately detect which of these activities are risky, then they might lend a helping hand and do specifically those tasks and let the humans focus more on simpler physical tasks or maybe more cognitively challenging tasks. So in order to do that, apart from the machine learning part, which was basically a lot of gathering of data and then figuring out which actions are being performed at what point of time, we also needed to use some kind of an ergonomics risk assessment model. And there are a few of them that are quite widely used in different industry sectors. So we chose one that is very popular in the construction industry, actually, where people do a lot of these heavy duty actions. So this model is called REBA. I won't get into how exactly it comes up with a score, but it has been around for a while and it has been found to be very successful in real world deployment. And it's also very easy and intuitive to deploy and interpret. So all that it gives is some score between 0 and 15, and you can categorize this scores into different kinds of ergonomic risk levels. And if we can associate that kind of a score with the current activity of a human, we would know where robots can come in and help. So this is the overall pipeline then for how we built this end-to-end system, where based on like the real-time skeletal reconstruction of the human posture and how they are actually performing the activity, we would capture all of that in a live stream video and do real-time processing based on spatiotemporal deep learning model that has been trained and learned from similar videos. So again, there are lots of technical details on what exact deep learning model we used, why did we choose those, and what kinds of features did we end up analyzing. But I don't think this limited time I have the option to get into all of that. But any of you interested, please follow up, or like I'll be listing some of the papers where we cover those in details. But just suffice to say that we combine this skeletal-based ergonomic risk assessment model with these end-to-end deep learning framework to do this real-time processing of within like a continuous stream of actions that a person is doing, what are the individual activities they are doing and what their corresponding risks are, so that you know where and potentially in the future which of those actions should be taken over by the robot. So in order to train a model appropriately, we relied on some already existing data sources, but we didn't find something which was close enough to the kinds of warehouse types actions that we wanted to really capture. So we did our own data collection and we recruited some volunteers, participants to do that. And we had like about 3 minutes worth of video for each of our participant. And one thing to note, which is kind of a technical issue with many of these action identification or segmentation methods, is they don't typically work that well with these long duration of a video. They work very well with shorter video clips. So we managed to extend the models to make them work for these longer duration videos with a pretty large number of action classes. And we showed like pretty good performance on this data set, as well as some other existing data sets for slightly different actions. So the top line numbers are that we got like more than 85% of accuracy, and also very importantly, our edit scores and overlap percentages are high, which means we are able to detect when exactly one action transitions to the other, because that's kind of key. And that's a big technical challenge with many of these video processing methods, that which is why they work well for short clips where you know you only have a few actions. But if you have a continuous stream of actions, which is what would happen in a logistics center, then you need to be able to reliably detect when one action or one kind of posture is terminating and a different kind of action, such as picking up an object and then bending to place it somewhere, that starts. So that is captured more through edit score and overlap, and we comfortably outperformed like the state of the art there. So we did implement it on an actual collaborating robot, and you can find more details in a couple of papers that are listed here. So switching gears, but still sticking to robotics, this is a current project that we are doing with the Navy. In fact, we have multiple projects on the same topic with the US Navy, which is still within the broad purview of human-robot collaboration, but the application is entirely different. And here we are getting into more of these multi-robot systems, and how where humans can still assist even if you have these multi-robot systems, especially for very challenging tasks. So here the challenging task specifically is on related to maintenance. So as you can imagine, for the Navy, they would have lots of these vessels or like sea vehicles. Some of them may be unmanned or autonomous, which would be deployed out in the ocean on actual missions, but even otherwise they might often be docked for like repair and inspection and so on. So whether it's on the mission or whether it's for actual during docking times, lots of maintenance work are typically required. And as you may also imagine, I can't like show actual figures, but these vessels are going to be pretty complex systems with lots of components inside them. Some of those are very, what we would say, confined, tightly confined spaces with lots of machineries that need to be inspected and so on. And also on the exterior side, you would have like a pretty large sized hull with lots of features there that also need to be monitored for like structural integrity and like performance degradation and so on. So none of these tasks are easy to pull off, not something any human would particularly enjoy doing, but right now they are who are doing all these things. It's not done by robots. It's done almost exclusively by humans who have to either crawl inside those tight spaces or they have to be those divers in these undersea environments in pretty bad conditions, sometimes in turbulent waters where they have to do this kind of a thing for often hours together. So clearly there is some scope of not necessarily entirely replacing or getting rid of humans, but definitely assisting them with the robots, or at least making robots do the actual like dull, dirty work, whereas humans can be more in a supervisory capacity, like monitoring the whole process remotely. So that's kind of the thought here. And of course, if we can pull it off, it would have huge impact in terms of the time, the efficiency, the robustness of these operations, and most importantly, I think in terms of not having those humans do the tasks that are clearly in hazardous conditions. So there has been some work on building these very customized robots which can like go and do very specific kinds of maintenance and repair tasks. So that's already in progress, and that has been going on for a few years at DoD. What we instead are trying to do here is that we want to take like very simple, cheap, commercial, off-the-shelf kind of robots with like open source packages and libraries that can be deployed easily. It does not require $1 million of investment to build something just tailored towards one kind of task. So that means we would be using like standard ground robots, some maybe crawling type robots, which you can just buy it on Amazon or any other site for a couple of $100, fit some, again, very popular sensors on them, mostly like camera based, because like there are challenges with many of the range sensors in these kinds of environments. Camera also has challenges, but it's okay for more shorter duration, like mapping. There it works okay, but for longer duration, so longer time, spatial horizon mapping, there are challenges there as well. But in any case, the whole idea is to have like very low cost alternative solutions where instead of having something that costs $1 million, we might have a bunch of these low cost robots that act in coordination to like perform these tasks. So right now we are kind of taking baby steps towards that eventual goal. And what I'm showing here is this kind of a simulation with just a single robot, but to give you a sense of the type of environments that it's supposed to be experiencing. So this is inside like a confined water tank, and there are many types of water tanks inside those marine vessels. So you can, as you can see, there are lots of those pipes and cables and vertical structures and all, and you have to pretty much inspect each of them. And what we wanted to show that the feasibility of this whole idea using just low-cost solutions with open source platforms and packages. So as you might expect from here from robotics, we ended up using ROS, and that's how, and this simulation is running on Gazebo, and it's showing the feasibility of doing it. Now, one quick thing, there is this yellow color structure here. So that is called a FOD, or a foreign object debris. And that is actually one of the big use cases for doing these kinds of inspection, that sometimes when these structures are put together, or maybe some big maintenance work has been done, inadvertently people might leave behind some tools, or and they might be something as small as like even a nail, or like a screw or a nut or a bolt, and but they, if they are left behind and then the vessel goes out on a mission, they sometimes have big impact in terms of what happens during the actual mission. So we do want to make sure that after installation, or after some kind of major human-led maintenance, all these foreign object debris are removed before the vessel is actually deployed. And that's kind of a very nice use case for deploying a robot. You don't want to send another human back again to look for all these debris that might be left behind. So what we ended up doing is we used state-of-the-art visual SLAM, but on top of that, we put in our own probabilistic mapping approach based on this Mahalanobis distance metric to identify which, from the real-time map, how much does it deviate from the nominal or expected map, and those deviating regions are then clustered and I characterize them as potential faults. So this is the overall pipeline. I'm not going to get into much details of it, but jumping onto the results, what we found is that we have a very high recall. If we run in a purely autonomous mode, it has a very high recall, but low precision. In other words, it's kind of like very conservative. If it's unsure, like it would label certain regions as deviating regions or candidate faults, but they may or may not be really faults. So it does a good job of finding everything, but finds the surplus or extra things. And that's where, like, remote humans who do not have to go into those tanks anymore, they can just sit at their desks and look at those images captured by the robot in real time and figure out a simple thing of whether it's truly corresponds to a FOD, or it's just part of the structure of these confined space, which was detected as a deviant region because of the ways, the stochastic nature of the processing and the sensor unreliability in sensing and so on. So it's still taking advantage of humans. So it's a cyber physical where humans are still playing a big role, but they are not being asked necessarily to do a lot of these hazardous tasks and can just contribute from remotely in a positive way. So we ran some human study trials and found very promising results. And currently we have a paper under review in RAL, IEEE RAL. Okay, so I think I don't have much time. So instead of going over like the two projects that I have listed here, I'll just quickly go over one of them, because this is kind of a very different domain in manufacturing. So I'll spend a couple of minutes there and then quickly end. So this does not involve any robot, and it's does not involve inspection or anything or any human assistance, but it's about composites manufacturing process, where right now, even though the processing itself is automated using something called automated fiber placement, the inspection is to a large extent still done by humans, because even though there is an automated inspection system in place through this camera-based image processing, as you can see, the images are very, very challenging, and the existing system in place does not do a good job of identifying basically these boundaries among the different ply layers, which does need to be detected very accurately to make sure that they conform exactly to the dimensional requirements of this part. And this again has a big impact in terms of the overall processing time and throughput and all of it. This is a representative sort of back of the envelope calculation. So considering how many such large composite parts you would have in a typical aircraft, and how many of those ply layers, which we call toes, there would be there. If humans have to do all those inspection, even if they can very quickly look at ET image and make a judgment call, which won't be always the case because people would feel fatigued and so on. But even in an ideal setting, it would take like hundreds of hours to do the inspection, which is how it is right now. And the reason, again, the existing system is not reliable, is not considered to be reliable, is because it uses a lot of these kinds of standard image processing methods where you can see it's all over the place. It has no clue where exactly the boundaries are. So what we ended up using is we took inspiration from biomedical imaging, where UNet is a very popular deep learning model, which does a good job of analyzing challenging images, such as identifying like lesions in like a large volume of tissues and pathology and things like that, without requiring a whole lot of training data and whole lot of human labeling or annotation. So we have kind of the similar challenge here, but in a manufacturing setting where we cannot recruit a huge number of experts to label hundreds of thousands of images, and the images themselves are very challenging. So we got about like 4,000 or so images that we could label and treat them as ground truth. And then we did some data augmentation and all, and built our own modified version of this UNet. And with that, this is kind of the summary of the result and now we could bump up the accuracy to as much as 99%, which makes it a lot more palatable for the manufacturers to actually deploy it in their production systems. And this is actually happening as I speak now. It's in the works of being deployed on a Boeing production facility. And we also have a recently published conference proceedings paper detailing more of the methods and the results. So I think with that, I'll conclude just by acknowledging some of the sponsors, a lot of them actually here for the various projects, and of course the people who have done the actual work, the students, and also my collaborators. So thank you again.
Thank you very much, Ashis, for presenting a very exciting project. We still have a minute left, so I will go quickly just ask a common question that most of all participants are generally interested in. The question is like, what are the emerging skills do you recommend for students or practitioners who want to basically enter the space of data science, machine learning, and AI?
Ashish, you can go first.
Okay, sure. So I think two things are required, like some amount of coding skills, but you can also acquire that quite a bit over time. So my own personal experience is that when I started working in this domain, and even robotics more than a decade ago, I wasn't that great of a coder programmer. So like with interest, time, and practice, you can be a lot better at it. But you need to have that interest and aptitude. And then something which is, I think, even more critical is these analytical bent of mind. So a lot of people might think of data science as these some kinds of magical black boxes or even gray boxes that you can just throw in some inputs and get outputs, and that might work in some very standard problems, or if others have already done a lot of the legwork in terms of encoding the problem characteristics. But if you have to tackle a new problem or make a real significant impact, you need to understand a lot properly, like the maths behind how these models work. So definitely the like background and experience or some level of expertise in these analytical models, and especially stochastic models, that I think would be key skills to have if you want to be successful in the long term as a data scientist.
I'll second that. I think sound fundamentals. So the analytical bent of mind that Ashish mentioned starts with very sound fundamentals, understanding the basics, right? So we get too caught up on these newer packages and newer ways of using some tool, etc. I think coming from academia, I think what is important is like making sure your fundamentals are very sound, so that how you enter the career is one thing, but how you sustain the career. Libraries change, languages change, but if you have this, if your fundamentals are very sound and you're grounded with the undergraduate course in this as well as the first graduate course, like understand it well, like not just like I apply to the problem that was shown, but I'm able to apply it to more general ways. That really, I think, if you can start there, that's usually a good starting point. Just being a computer scientist, the types of things I see, they definitely require some programming. But the advice in that sense is similar. Don't get too caught up with one package, one library, one language. Being able to realize, so understand concept, realize it in code. And I keep insisting with my students, if I say Python, you should be able to program Python. If I say C, you should be able to program. Like, I think realizing the language is one thing, but like if you're able to understand and realize it in something, that is the key. The fundamentals are essentially the key.
Thank you very much, Karthik and Ashis, for your remarks. I would also like to take some time to thank both of you for taking out your valuable time and spending that with the audience that we have. I really personally appreciate that. And with that, we will conclude this webinar. But for all the participants who are there, if you want to have a recorded version of it, we have posted the link of the YouTube channel where the videos will be posted. So you can go there and you can subscribe to that channel, and you can see this video and also all the other videos that has been posted. So with that, thank you everyone for participating, and we look forward to the next webinar, which I will post soon on LinkedIn. Have a great day.
Thank you.
Bye.
Thank you.
Thank you.